Good day, everyone. Today I'm going to walk you through an exciting and timely study published in AGU Advances by Marshall and colleagues in 2024. The paper studies and focuses on the 2021 eruption of Fagradalsfjall in Iceland, examining it through the lens of petrology and geochemistry. This eruption was not only scientifically rich, but also visually spectacular and geochemically revealing. It provides researchers with an unprecedented opportunity to study deep crustal magma processes in real time. The authors took advantage of this by collecting and analyzing the extensive suite of lava samples over the course of the eruption. To set the stage, let's quickly review the eruption itself. Fagradalsfjall eruption in March 2021 and continued through September, lasting almost 6 months. Located on the Janes Peninsula, this was the region's first eruption in about 800 years. It produced continuous, low explosivity lava flows with little ash, making it relatively safe and accessible. Because of the favorable conditions, both geological and logistical, it became one of the best monitored volcanic events in Icelandic history. The eruption occurred in the tectonically active rift zone, where the Eurasian and North American plates diverge. This context is key to understanding the magmatic dynamics of the study covers. The study has three primary goals. First, to trace the origin and transport path of the magma, where exactly it came from on the Earth's interior, and how it rose to the surface. Second, to monitor and understand how the chemical composition of lava changed over time. Did the magma stay the same throughout, or were the variations that tell us something about the system's evolution? And the third is to use the eruption as a window into the workings of deep crustal magmatic systems, how they are structured, how they are behaving during the sustained eruptions, and what signals they produce that we might one day use for better volcanic forecasting. To achieve these goals, the team used a combination of field sampling and laboratory analysis. Over 200 lava samples were collected throughout the eruption, capturing both early and late eruptive phases. Petrological methods include thin section analysis to examine mineral textures and crystallization histories. Geochemical techniques analyze both major elements like silica, iron, and magnesium, and trace elements such as rare earth elements and incompatible elements like titanium. In addition, isotropic ratios of strontium, neodymium, and lead were measured. These isotopic signatures are crucial for tracing magma sources and understanding how different magma batches might be or might have interacted. This multi-pronged method provides a high-resolution look at both the magma's chemistry and its origin story. One of the study's most important findings relates to the depth and structure of the magma plumbing system. Unlike the simple model of shallow magma chamber feeding the eruption, the researchers found that the magma originated from much deeper, about 12 to 15 kilometers beneath the surface. This implies a vertically extensive plumbing system with magma rising vertically directly from the lower crust. It suggests that the presence of long-lived lower crustal magma reservoirs that were actively interacting and mixing. This challenges older models that assume such eruptions only involve shallow system and simple melt transport. So, in a sense, what looked like a small and slow eruption at the surface was actually fueled by a deep and dynamic system below. The second major finding centers on how the lava's chemical composition changed throughout the eruption. In the first 45 days, there was significant variation in trace elements, particularly titanium, lanthanum, and yttrium. These shifts pointed to the mingling of multiple magma batches with different geochemical fingerprints. After this early stage, the lava chemistry began to stabilize. From about 50-day onward, the trace elements concentrations became more uniform. This suggests that the different magma sources had mixed and equilibrated, leading to more homogeneous smelt being erupted. The study interpreted this as an evidence that magma mixing occurred in the lower crust over weeks to months, providing a real-time view of how substances processes affect erupted or eruptive products. To support the chemical findings, the author also looked at isotopic data. Isotopic ratios are like fingerprints; they can reveal whether magmas come from the same source of different parts of the mantle. At the parts of the eruption, the isotopic ratios show considerable diversity with clear differences in strontium and neodymium ratios between samples. This confirmed that multiple mantle-derived melts were involved. Over time, the isotopic signatures converge toward a single, more uniform composition. This mirrors the chemical and reinforces the conclusion that active mixing and homogenization occurred within a deep crystal reservoir during the eruption. So, what does all this mean for volcanology more broadly? First, the study shows that even small, seemingly quiet eruptions can have deep and complex origin. This highlights a challenge for volcano monitoring. Traditional shallow signals like ground deformation or gas release might miss important activity deeper in the crust. Second, the rapid evolution from the heterogeneous to a homogeneous melt over just a few weeks shows how dynamic magma system can be. Eruptions can be influenced by deep processes that act on surprisingly short timescales. And third, this eruption provides a model for how magmatic systems on rift environments behave. It suggests that deep, long-lived, and compositionally diverse magma bodies can coexist and feed eruption through sustained mixing. The results of this study are not only important for Iceland but also for our understanding of rift zone volcanism worldwide. Similar deep crystal magmatic behavior may be occurring in places like East African Rift, the Galapagos, or even certain parts of Hawaii. This kind of detailed, time-resolved petrological and geochemical monitoring is rare, but it is essential. The 2021 Fagradalsfjall eruption offers a benchmark for future studies, especially in linking subsurface processes with observable eruption dynamics at the surface. It's powerful reminder that we need more integrated geophysical, geochemical, and field-based monitoring system if we want to fully understand and anticipate volcanic behavior. 2021 Fagradalsfjall eruption was more than just a photogenic event in Iceland. It revealed that deep crustal processes such as magma injection, mixing, and homogenization can play a major role in shaping even modest eruptions. The study by Marshall et al. Shows that magma can ascend rapidly from great depths and that the chemical signals that process are visible in eruption within days to weeks. This research not only advances our understanding of Icelandic volcanism, but also sets a new standard for how we monitor and interpret eruptions and rift zone around the world. Thank you so much for listening to this presentation. Have a great day, everyone.